Hello everyone. It's great to see you joining today. Welcome to New Twins webinar. I am beyond excited to share the stage with Francesco, our CEO, co-founder that has been running the company for the past 6 years. I am Andrea Pasqualini. I am the head of business development, and I am happy to guide you on what we will be discussing today. For years, thermal management has been treated mainly as a protection problem. But what if temperature could become an active source of intelligence? What if embedded systems could understand the true internal thermal state of the motor in real time without relying on physical sensors? What we're going to show today is how the embedded intelligence that makes it possible. We will discuss the limitations of traditional approaches, the technology behind real-time digital twins, and how can these unlock higher performances. Now, let's start with the problem that the industry still faces today. What we are seeing by collaborating with our customers is that most control systems still operate with very limited visibility. In fact, the motor is often treated as a black box. Controllers rely on few measurable signals, while the most critical thermal states inside the machine remain absolutely invisible. Because those internal temperatures cannot be directly observed in production environments, the industry compensates with conservative assumptions. This creates 4 major limitations. The first one is that conservative safety margins. Hardware is over-designed simply to survive worst-case conditions. The second one is the limited observability. We are estimating internal behavior indirectly using external proxies. The third one is the static derating strategies. Power limitations are applied generically, regardless of the actual thermal condition of the machine. And then the final one, not for importance. In fact, high-fidelity physics models exist. We all use them, but they're usually far too computationally expensive to run directly on the embedded hardware. So the industry is facing a trade-off, either accuracy or real-time execution. Our goal as New Twin is to remove that trade-off completely. The key idea behind the concept of, well, instead of concept, I would say the technology of the embedded intelligence is actually quite simple. In fact, instead of guessing the thermal state of the motor, we reconstruct it. New Twin's approach combines reduced order physics AI enhanced calibration, and embedded deployment into a single real-time system. The center of this architecture is a real-time digital twin running directly on the microcontroller unit. This digital twin continuously estimates critical temperatures such as the rotor magnet, the stator winding, and internal thermal dynamics that are otherwise impossible to measure directly. This, of course, changes the role of thermal management substantially. Thanks to this technology, temperature is no longer just a safety constraint, but it's rather a real-time control variable. The technology can enable better motor protection, smarter derating, improved efficiency, faster development workflows, and embedded deployment without adding physical sensors. We are not replacing the control systems, of course, we are augmenting them with physical intelligence. Before passing the word to Francesco to dive deeper on the technology, maybe we can spend a couple of words of who New Twin is. New Twin was founded in 2020 in Padova, which is a city located in the northeast of Italy. And our mission is quite unique, and is to enable real-time thermal awareness inside the embedded systems. Our expertise combines mainly three domains that traditionally operate separately. In fact, we have expertise in multi-physics simulation, embedded control systems, AI, and machine learning for physical systems. The result of this expertise is Twin Fabrica that we will see shortly. Twin Fabrica is our software platform that was thought and developed to develop, validate, and deploy embedded thermal digital twins inside the microcontroller units of your components. What makes the product unique is that the workflow is designed end-to-end. In fact, in Twin Fabrica, you can start from a CAD geometry and finite element simulation, and it will bring you with a unified workflow all the way to deployment on embedded hardware. Currently, we are mainly working with OEMs, tier ones, semiconductor companies, and electromechanical system manufacturers. And the common challenge that we are seeing with these customers is how do we bring physical intelligence closer to the real-time control. To give you an overview briefly of the customers that we are collaborating with, I would say that our footprint is quite global. And this is because the pain point that we have been discussing is broadly present in many different countries and industries. Thermal visibility, in fact, is a key bottleneck. Now let's see which are the different applications where the technology can be applied. Today, the webinar will be focused on eMotors, but the approach can be applied to different applications as well by using the same methodology in inverters, batteries, onboard chargers, power electronics, and other thermally constrained embedded application. You can improve the thermal visibility and therefore the controls and the rating strategies of your components. As mentioned, super briefly, Twin Fabrica is the engineering platform that powers and empowers this entire process. It allows us and our customers to transform high fidelity physics into executable embedded intelligence. It's mainly used by ourselves, but it's also used by our customers. The workflow looks like this. Everything starts from the physical system, from the CAD geometry that is imported directly into the platform. Second, the finite element simulations are created to capture the thermal and physical behavior of the systems. Third, model order reduction techniques compress those high fidelity simulations into lightweight real-time models. And then there is the AI piece, the AI calibration that is used to refine the model accuracy using ground truth experimental data. The final step is the export. The final code is deployed directly into the target embedded hardware. I think it's important to mention that the importance here is not the individual steps, it is the continuity of the workflow. In fact, instead of having disconnected tools and fragmented validation loops, Twin Fabrica and its process becomes integrated from simulation to the embedded deployment. Of course, you can imagine how this workflow dramatically accelerates development cycles while at the same time improving consistency between virtual and real-world behavior. Now that I saw that some people joined, maybe we can revisit what we have seen in the first slide, so the original problem, with a slightly different perspective. The challenge, as we mentioned, is no longer only thermal protection. The real challenge that we are seeing today is thermal visibility. When internal physical states remain hidden, systems are forced to operate conservatively. But once the embedded system gain real-time thermal awareness, entirely new optimization strategies can become possible. Control system can become adaptive, and the rating can become dynamic.
Thank you, Andrea, for the kind introduction, and thank you people joining this webinar on, let's say, motor efficiency optimization for real-time control. I'm Francesco. I will present you today the technology overview of NewTwin and the workflow applied to electric motor case. Great. So as Andrea mentioned, in NewTwin, we have developed Twin Fabrica, which is the first engineering software platform to basically bring simulation on the edge, which is the main mission of our company. So you can think about Twin Fabrica like a software layer that can take over the job of your high fidelity simulation models that usually you use, define, and design before the production, no? Before the real motor. In this case, it's a concept from the white paper into the production case. No? We usually start from this model. It means that the geometry is frozen. You already have prototypes, you already have a test bench validation running, you already have created the first samples, the sample A, sample B, and you have oversensed the special sample of electric motors in order to acquire data for functional testing, endurance testing, and so on and so forth. This is the exactly, let's say, time frame where our technology comes in. And the main scope is to help our customer to integrate inside the microcontroller units of their electric drives, in this case, real-time high-fidelity models that can predict special variables like power losses, like temperature in the windings, like temperature in the magnets. Now we will see a short demo of this. Why this information is relevant? Because bringing simulations on the edge, basically we can enhance information on the electric drive, and our mission is to make products more efficient, more performant, and increase the safety of them. So basically, with more information, you can take smarter control decision, and you can push with the performance of the electric machine in a completely safety way. Let's see the workflow. Let's see the process of our technology and why we claim that thanks to this platform, we make, let's say, scalable the process of bringing high fidelity simulation models inside the microcontroller units. So everything starts from the import of your fidelity simulation. So it means that the geometry is already present. Here I can show you an example. Inside Twin Fabrica, there are many software libraries. So one of them is a CAD kernel that allows you to do all the Boolean operation in order to import the step file, but also of other, let's say, CAD kernel file format. This is one of the input that you can select for your final geometry. In this case, this is an IPM with interior permanent magnet, airpin technology. It's oil spray cooling technology for this particular motor concept. There is another input that it's the mesh file, so you can directly import the mesh file from ANSYS Fluent, Console, Star CCM Plus, doesn't matter. Or you can basically create the mesh inside Twin Fabrica. So if you want to start from the geometry, there is no problem. Inside Twin Fabrica, there is also the mesh generator engine that allows you to create a 3D mesh for finite element analysis and to solve the partial differential equation related to the heat transfer. Why the heat transfer? Because it's the temperature, it's the state variable most critical for and most tied to safety and to performance. No, in particular for oil spray technology, you would like to estimate the hotspot across the windings configuration. You would like to predict the temperature in the magnet in order to avoid the demagnetization and so to lose the efficiency in an irreversible way. There are many reasons why temperature is very relevant for electric drives, mostly in the automotive, but not only. And also the problem is that the state of the art of hardware, so the classical NTC that is placed in the winding or in the stator stack, is not enough to predict the hotspot dynamics, the hotspot, let's say, resolution across this motor technology. And most of the time, you cannot measure directly in the spinning part, so in the rotor where you have the magnets. However, our companies, they have very good models. So in fact, the first step will be the integration inside Twin Fabrica of the high fidelity simulation model. And with that, of course, you can perform like we can see in this case, you can compute changing boundary condition, material properties, heat sources, etc., etc. You can perform the high fidelity simulation, so you can solve, in this case, the partial differential equation related to this finite element model. It means that inside Twin Fabrica, we also have the FEM solvers in order to take this into account and to solve the distribution of the temperature, so the heat transfer equation, in order to get the temperature solution across our electrical machine. So as you can see, this was just for the sake of time, just a steady state simulation computed in my laptop, which means that with Twin Fabrica, yeah, you can simulate also transient, frequency domain, steady state, whatever, and you can use it in order to double check if the input of the model has been set properly. So if you set properly the material properties, the heat sources, and the boundary condition. However, this is just the first step. The scope is to basically create a model that can replicate real-time this kind of behavior. So unfortunately, this model is quite good. It has, in this case, more than 1 million of degrees of freedom, coinciding with the node of the mesh in describing this geometry, no? But these kind of models, for memory reasons and for computational, let's say, requirements in order to solve the algebraic equation of the finite element analysis, inside a microcontroller unit, of course, they don't run, right? There are tools, there are methodology, and inside Twin Fabrica in particular, we have implemented a nonlinear model order reduction library, which is the first commercial nonlinear model order reduction library available in the market, which can easily tackle, for example, the radiation, which can easily tackle, for example, the advection. So considering this kind of physics also in the finite element analysis of your model, as well as the temperature dependency, you know, so material properties that they depends by the temperature, as well as the heat sources. So in this case, using our model order reduction, you can obtain a model of just 31 differential equation, which is basically describing the full order model of more than 1 million of degrees of freedom. And what you can do inside Twin Fabrica is the analysis. So basically you can evaluate the fidelity of this reduced order model respect to the full order one. So for example, you can run several conditions, even here, steady state, frequency domain, or transient, in order to double check if the accuracy of the reduced order model respect to the full order one, for example, changing once again boundary conditions, heat sources, material properties, and so on, it is good enough. So in this case, you can see plotted the error. So in every single node, you can see the error between the full order model and the reduced order one. And if you go here, you can instead see the temperature distribution of the full order model with certain boundary condition and the heat sources, and the temperature distribution solving the model of just 31 equation, but then projecting back the solution in the full mesh in order to get the resolution of the gradient temperature. So let's say this is a kind of analyzer of the fidelity of the reduced order model respect to the full order ones. Let's say, so how good is the surrogate model, the compressed version, in order to, let's say, address the real-time feasibility inside a microcontroller unit? Because now this model size is, let's say, quite manageable for a microcontroller. And you can compare the fidelity of this reduced order model on several, let's say, simulations. Repeat, you can change many things, whatever you want. You can do your sensitivity analysis respect to the full order one, so respect to the first high fidelity model. However, this is not enough, right? Because we all know that the high fidelity model, the design one, they are good, but they do not represent the model as manufactured. Why? Because maybe there are some nonlinearities that have not been taken into account. Because I don't know, the heat sources, so the power loss distribution, it has some uncertainties or some error respect to the reality, or because some material properties, they are not known 100%. So there are many reasons why when we go on the test bench and we measure with a thermocouple, for example, across this winding, the time let's say, behavior, the temperature behavior of the measurement setup and the experiment and the simulated one, they differ, no? They have some error. There is some residual, and because doesn't exist, let's say, the perfect simulation, right? So the fidelity that the reduced order model can achieve in its first instance, it is, let's say, compared using the ground truth that are simulations, so the full order one. Now we need to move a step ahead. So we need to calibrate this full order model or the reduced order one. Of course, it's much cheaper from a computational point of view to calibrate the reduced order model that still, let's say, represents, it's a physics-based representation at the end of the full. So what we need to calibrate? To calibrate, we need, of course, in the first instance, to place sensors in the exact position where the real experimental setup, let's say, it's measuring. So, for example, in this case, we can see that in this particular case, we are positioning the virtual sensor. Let's say we are selecting the node of the mesh as close as possible where in the real test bench setup the thermocouple has been soldered. And why here there are several sensors? Because in this case, we are talking about a special prototype that the customer has used in order to collect the data, in order to do all the functional testing, no? And why they are measuring so many, let's say, sensor point in the stator winding, mostly in the end winding and in the core, because this coolant system, it was a noise spray one. So very hard to simulate, let's say, the oil spray CFD to get the right heat transfer coefficient map. In this case, the customer has preferred to, let's say, get some experimental good data set. So they did a really very good campaign. Checking the temperature in multiple points. In this case, they have generated, let's say, many virtual thermal sensors, because the scope of the customer was to have all these virtual thermal sensors then in production, but not with the real thermocouple, but just with a piece of software. So from here on, the next step would be to transform a model as designed into a model as manufactured in terms of accuracy. We need to achieve the industrial grade accuracy to rely on virtual sensors like if they are the real one, okay? So in this case, yeah, the first step was to place virtual sensor exactly in the same geometrical position where the real sensor setup, let's say, has placed the thermocouple, the PT1000, whatever it is, the sensing technology that you're using in your test bench. But the next step, it would be to, let's say, import the test. So to have a very good characterization. In this case, the customer usually they select multiple points across the let's say torque speed profile of the electric motor. So different speed, different torque profile. They are transient simulation. We can see in this case we can open one. You can find the electrical variables that will be the input for the power loss calculation, for the heat sources, basically for the thermal model to predict the thermal behavior of the system. And what you can see, for example, is the, let's say, different, I can enlarge the screen, behavior of the stator point in different point and also the rotor, given certain ID, IQ, and speed profile, okay? So these are the classical data set where you have the phase on and the phase off in order to record the free evolution of the system. This is a classical measurement setup and let's say temperature recording and electrical variable recording in order to use this data to calibrate our model. So once you have imported the data, the next step would be to calibrate. So we will calibrate the reduced order model through Twin Fabrica. So inside Twin Fabrica, there is also an optimization library, in this case, which in first instance will calibrate the physical parameters, so material properties, heat sources, boundary condition, let's say potential uncertainties that you want to model, to get the right accuracy respect to the real test bench. However, sometimes just a physical calibration, so just, I would say, moving material properties and boundary condition uncertainties, it's not enough. Because many of the time, mostly for the electric motor case, in the microcontroller unit, where you have to implement your model and when you have to control the final thermal behavior of your, let's say, electric motor, you don't have some relevant simulation, some relevant information to simulate the thermal model. Just an example, the coolant flow, or the pressure of the oil, or the temperature of the oil itself. Most of the time, these variables that are relevant to model the boundary condition of our model, they are not available, and they are not constant. So we cannot imagine to place them like a constant value of the coolant flow and the coolant temperature, for example, to impose it, I don't know, 10 liters per minute and 50 Celsius degree, for example, because in the real application they are time varying and they are most of the time unknowns, in the sense that these two variables in the microcontroller unit where the final model must be implemented, they are not known. So in this case, you have to do something more. In this case, you have to enhance, you have to empower, if you want, your physics-based reduced order model with an edge AI one. So with the specific, let's say, data-driven model, in this case, and we have a set of libraries of them that you can directly use together with your reduced order model in order to, in this case, train the parameters of this edge AI model to infer the unknowns, or let's say to the residual between the calibrated physics-based model and the ground truth data. So if you want to achieve really a high accuracy into your system that is relevant for the final scope of this project, that will be to improve the efficiency of the electric drive in this case, and we will see in a moment how, it's important that you calibrate these, let's say, artificial intelligence network models that are together coupled using Twin Fabrica with the physics-based reduced order one in order to achieve the target accuracy of the customer. Usually our target is plus minus 5 Celsius degree for all the sensors that the customer they want to develop and considering, let's say, all the conditions, so changing torque, speed, current D, current Q, the coolant flow, the coolant temperature, and so on and so forth. So in this case, let's see if we can execute, yes, let's enhance the, let's say, reduced order model with an AI one that we have already trained. In this case, also this inside Twin Fabrica, you have available the trainer of these models. So in the same identical platform, as you can see, you have many libraries, so very, let's say, large technology stack of software where you can basically manage from the import of the CAD to the code generation of the firmware to program your microcontroller unit that we will see in a moment. Passing through also the training, so there is also the artificial intelligence model trainer inside Twin Fabrica that you can directly use with no code. Like in this case, you can set which, let's say, test from the ground truth measurement using calibration and using validation, and you can set some of the hyperparameters and press train. And I would say a couple of hours, 1 hour, it depends on the data set, let's say, and on the, let's say, size of the model library that you will choose. It's capable of calibrating the parameters of the network. It could be different kind of networks that you can select, attached with the physics-based ROM in order to enhance the accuracy. So now, if we can have a look in violet with continuous line, we have the, let's say, let's make a zoom, in order to get the error during transient, for example, in continuous, you have the IR camera recording, and in the dashed line, you have the model estimation. Of course, you can see the error in all the temperatures. So we can see, for example, in this case, it was an oil spray cooled. If the distribution of the temperature is preserved, as you can see, the model is quite good in predicting the temperature compared to the one of the NTC or the thermocouples. And if we change, for example, test, I don't know, we can go higher with the speed. Of course, the accuracy is preserved. In this test, maybe also the coolant flow was changed. Who cares? It was not, let's say, an input of our model. However, this, let's say, dashboard get you the feeling of how good is your model, how robust it is, and if it is industrial grade. So once you are satisfied, the last step to do is the export. So you can go back into the first, let's say, dashboard here, and you can export the model usually or using a Simulink white box block that can be directly plug and play into your, let's say, I don't know, motor control Simulink simulation model, or we can directly generate the C code, so a library, in this case, a firmware library that can be easily compiled in order to program your microcontroller unit with the documentation and the library in order to integrate the final model into your hardware system. So this was just a recap of, let's say, how to in Fabrica operate and why it's relevant to get a model that is capable of predict the temperature in the hotspot, in this case, the end winding and the core winding, but also in the magnets. And why it's relevant? It's relevant because at the end, what we want to do is we want to unlock the motor efficiency, right? So using the same hardware, what we want to obtain is a piece of software layer that is capable of managing properly the ID and the IQ current references, such that you still, let's say, satisfy the PI controller of the speed, so you still satisfy the torque request from the, let's say, slow loop controller of the electric drive, but you increase the efficiency. Why? Because most of the time, our customer, let's say this is the goal, no? We want to improve the efficiency and we want to have a very good thermal management of the hotspot and of the temperature of the magnet. To do that, usually our customer, what they do, they have lookup tables. So you go on the test bench and you define, let's say, very large lookup tables, 4-dimensional. So you have ID, IQ measurement, the speed, you measure the temperature maybe in the NTC, in the stator, and you try to move ID and the IQ on the test bench in order to, let's say, record, which is the torque request, but let's say with the minimum loss in the system, no? Other customers, instead, they say, no, I go, let's say, in a more raw way, in the sense that for me, the minimum loss is the MTPA, so the minimum ampere in the system, so the max torque per ampere. However, this is not true. Let's say it's not true for all the points, at least. So, for example, when the speed is in a medium range and torque is low, which is quite the case for the automotive, let's say, sector. It's an operating point that usually where you spend a lot of time in the lifetime of the motor itself. The MTPA point is not the most efficient one, because maybe the iron losses and the magnet losses, they count more than the joule. So you prefer to change the ID and the IQ in order to, let's say, move in another point of torque, but also preserving the same torque, but minimizing the iron and permanent magnet losses. That was the scope. Most of our customers, they do it by experiments. Others, they don't. They go just MTPA and field weakening. However, the input of these lookup tables, it's always there is also the temperature, because the temperature of the magnet, that is not constant, it's time varying, of course, influence the flux, and so all, let's say, the electromagnetic map, no, that you can have. So even if you have a very good and high resolution and calibrated by means of real experimental results lookup table, and you implement this, let's say, huge lookup table inside the microcontroller unit, most of the time you're not precise enough if you don't have a precise thermal model predicting magnet temperature and winding temperature. Why? Because it's relevant in order to, let's say, place the right point inside this LUT. It's the input. So what we propose instead is to implement our model. So instead of having lookup tables, at the end, our, let's say, reduced order model process, the input is the power loss. So we still have a power loss model that is an analytical version of the losses distribution inside the system that can be quite well calibrated on the test bench, at least the total losses. The distribution will be validated through the thermal behavior. And you can basically use this model in closed loop control to enhance the efficiency. And now we will see basically how we do that. Once you have finished with the model generation, as I've shown before, it's quite easy to generate C code. And this C code will be a software layer that can be, let's say, quite not invasive for your, let's say, motor control strategy, in the sense that we do not touch your MTPA, we do not touch your PI controllers, we just sit on top, in the sense that there is this firmware layer that can be easily implemented within a task of 1 millisecond or 10 milliseconds of your electric drives, and will act like this. So basically, it will take in input the ID, the IQ, the speed, and the temperature of the unique sensor motor you have there. And as I mentioned before, inside there is the power loss model and the thermal model that you will easily let's say, export from Twin Fabrica. So it's a piece of library that can be directly plug and played in the task of 1 millisecond. The output of this model will be the power losses distribution and also the temperatures of the magnet and the hotspot, counting for all the virtual sensors that you have modeled inside Twin Fabrica. So you can really try to track which is the hotspot in the system and to control it. And we also have the control logic. So it's the rating strategy that is taking in input the total losses and is changing the ID and the IQ in order that you hold the same identical torque for the system, so you satisfy the speed request basically from the PI controller, but moving the current, let's say, reference in order to move in the point of minimum loss. And this is the kind of control that we call mean loss per torque. And it is only possible if you have a very good power loss model. Could be also your lookup table potentially, but also a very good thermal model running in real time, because it's the input, for example, of your lookup tables in order to decide what will be the right correction for the ID and the IQ references into your electric drives. Now, the same identical, what we see here, B, the same identical control logic algorithm can also be used as is for the derating, in the sense that since inside the input of this is also the temperature in the magnet and the temperature in the winding, inside the control logic there is a closed loop PID controller that can be implemented. It's already implemented, but can be selected by the customer which strategy to choose in order to, let's say, derate, in order to limit the current of the system. So also in this case, also to limit the speed. So you cannot push with the maximum acceleration if you're risking to overheat the motor. Otherwise, you compromise the safety in this case. But this allows you to have a closed loop control on the hotspot. And why this is relevant? This is relevant because many of our customers, they are using safety margin. So since they know that in production it is quite hard, and the real-time models that they are implementing, maybe it is a thermal network, I don't know. However, for oil spray motor cooled, it's quite hard to manually design thermal network and to manually calibrate them. However, since they know that the accuracy is not good in all the operating conditions, they apply safety margin for the insulation and thermal class of the system, which means that they are compromising the current capacity and the torque capacity of the hardware itself, just with the software protection. To make you an example, in some cases, our customer, they are using also safety margin of 20 degrees with respect to the real hotspot that is defined by the insulation class of the hairpin. So the last point is the magnet. Magnet temperature estimation is really hard because at the end of the rotor, it's like a separated system with respect to the stator. They have different dynamic. I mean, it's quite hard to estimate properly a magnet, the magnet rotor temperature. So you need a very good model that runs in real time that is capable also to predict very well the temperature during the classical on-off conditions like the automotive one. So you need also a model that is capable to manage the initial condition calculation. And inside our control logic and our thermal model, everything is directly managed with the plug-and-play solution that the customer can directly test into their test bench. The only, let's say, effort that they need to do is the import of the test inside to Infabrica and the import of the high-fidelity model inside to Infabrica to generate the, let's say, real-time thermal model of the motor. The rest, it's already there. It's a plug-and-play solution that they just need to be tested. The entire real-time thermoelectric optimization layer here, it's running on a, let's say, standard reference for the automotive. It's the Aurix of Infineon TC387. And the execution time of this library plus the motor, electric motor model, it has an execution time within that platform of less than 100 microseconds and a memory footprint in terms of parameter smaller than 40 kilobyte. So more than eligible, for example, for the implementation in the 10 millisecond task in order to manage, let's say, the rating algorithms on the current, because it covers less than 1% of the task and you don't risk to compromise the real-time feasibility. So how we work with the customer? Usually we align on the motor, of course, that they have to have at least close to production. So there must be, for our customer, available a prototype that is oversensed in order to collect the data, or maybe they have already data inside let's say, their facility on previous electrical machine, or let's say on the one selected to working together. This model must be shared, or we can directly deliver to Infabrica in the case customer they don't want to share with us, let's say, relevant geometrical, let's say, data. It's not a problem. We can work in the other way around, in the sense that you will use to Infabrica and we will support remotely. In that case, we need also information on the microcontroller in order to, let's say, give you the right support for the implementation of this firmware layer. You will see it's quite, we have all the documentation and it's quite easy, the implementation inside microcontroller of any family. And then we need to agree on a test bench, let's say, integration and test, because the main, let's say, thing that we would like to prove in order to have a tangible value measurement of our technology would be the, for example, a VLTP class 3 drive cycle run without this software layer and with this software layer in order to measure the efficiency gain. So basically the energy that we have saved serving the same identical mission profile in terms of speed and torque. That would be one of the KPI, because the other one, it would be, let's say, the test for the derating. So we can see how effective is the closed loop derating control using, or so always with and without this red firmware layer, in order to have tangible results for validation and for the go or no go into production with this firmware layer. So the first question is, have you looked at leap frequency optimization in induction machine to obtain optimal efficiency performance? Well, very nice question. In this case, not specifically, but with the induction machine, we have this kind of, I think it's quite related. You are in the field-oriented control using induction machine only if you can estimate properly the rotor resistance of your induction machine. However, rotor resistance, once again, it is temperature dependent. So if you have a very good thermal model, you can estimate in real time the rotor resistance with high accuracy, and you are effectively in field-oriented control for the entire lifetime of the electric motor itself. Otherwise, if you are just measuring the rotor resistance, for example, when the rotor is at 70 degrees, you will be in field-oriented control only at the instant where the rotor, it is exactly at 70 degrees. And this is quite easy also to be tested on a test bench, because if you ask a step a square wave, let's say current, Q current with the induction motor, you should record a square wave torque response if you are in field-oriented control. If you're not, like in the case where there is some error in the rotor resistance estimation for the field-oriented control algorithm, so to increase efficiency and performance of the system, in that case, you will fail, and you will see that with a square wave of Q current, the response in torque will not be, let's say, a square wave, but it will be with some delay or with some overshoot. That is the classical validation from the state of the art to see if effectively you are in field-oriented control. Another relevant point from say what we have seen so far in the state of the art, which is people is working on quite similar solutions within their business unit with very smart engineers, long software tool chains. Most of the time, the real-time thermal model, they are made by hand, in the sense that there is the smart engineer designing manually an equivalent circuit and made by resistance and capacitance, and these parameters will be calibrated through test bench experiments. Then they will obtain a reduced order model like this, a thermal network at the end that can be used in real time in a microcontroller unit. But this is usually a long process done manual. So once we deploy to our customer to Infabrica, this is quite useful because minimize the time and helps these engineers to basically bring their high fidelity simulation model exactly that one without losing a resolution on the edge and calibrating them with the AI in order to cover not the model inaccuracy. The model maybe is super accurate, but the input uncertainties, because as I mentioned before, one of the main problems is that coolant flow and coolant temperature, they are not known once you are with the microcontroller unit. So there is another question: can you model EEE SM synchronous machine, electric synchronous machine? Yes, absolutely. So it's with the machine with the salient pole can be of course modeled, and we can treat them. I'm curious if this model needs to be pre-trained in a dyno test. For sure, in the sense that the Infabrica use your model. So we do not design for you. We take your design, we compress them enough, but then to achieve the accuracy that for you is suitable for production, you need to collect data in a dyno test. In this case, to use this data as ground truth for the calibration and the validation of the real-time model, also to, let's say, measure the robustness of it. And once you have done this, let's say, calibration process, you can, let's say, return back on the test bench. You can finally validate among other operational points, for example, never seen during the calibration, in order to measure if the model that you have obtained, it is suitable for production. And you can rely on it, like if it is a real sensor implemented in the magnet, for example, or many real sensors implemented across the winding, but without the hardware. So without the thermocouple, it's just a piece of software implemented in your microcontroller unit. So the answer is absolutely yes. This is a prerequisite usually, but it's the customer that decide to go or not go in production. So depending on what is for you the right procedure to trust in the model. Okay, we are just enabler and we give suggestions, of course, but it's always the customer that decide if to go or not go in production with a piece of firmware. And if, for example, instead your high fidelity simulation model has already been trained with many test experimental data or calibrated done in the dyno test, so it's already very good in terms of accuracy, and you really rely on that, no, we don't need, we just need to reduce your high fidelity model and we can directly implement it into the microcontroller unit. To answer your question.
Thank you very much for joining today. Hopefully everything was clear enough. Of course, we could have gone a bit further with explaining the technology, the benefits, customers, and so on. So in case you are interested, of course, get in touch and we will be happy to continue the conversation. Thank you, Francesco. Thank you, everyone, and see you at the next webinar.
Thank you very much. See you.